sum of two trefoils. And so it's a particular kind of diagram that I got from the standard picture, but the connected sum idea is a little bit more general, but for the homework, just think of it this way. And if I wanted to, I could do the same thing with 3. So if I wanted to connect the sum of 3 trefoils, I could do that. I guess I'd start. I'm a little sloppy here, but you know, it's all the same up to planar isotype, right? So here's the connected sum of 2 trefoils. So let's do the connected sum of 3 trefoils. And then, you know, just keep doing this. Anyways, the point of why I'm bringing this up now is that one of the exercises in the book that's not assigned but still fun to think about is there's a claim in the book that if you can tricolor a projection and then you do the connected sum thing with another projection. So say, we know the standard picture of the trefoils tricolorable because we did it. But then if you take a connected sum with something else, even if it's not the same, the book claims that that resulting picture should be tricolorable. So in particular, this should be tricolorable. So what can you try doing? What you can do is you can take one tricoloring that you did here, right? And then here was white. Well, when you connect some like this with this other, junk, just make it all that one color. Just make it all one color. See, the thing is, making everything one color always satisfies the second condition for tricoloring. It's just to use more than one color thing would go awry. But if you already have a picture like this where you use more than one color and then this loop now gets sort of connected up to some other picture, no matter, like imagine it's just something complicated, to be like one of the more complicated pictures in the book. We'll just color all that junk one color. You already have 2 colors, right? So that's one of the exercises in the book that you might have thought of. But anyways, of course, the connected sum of 2 there's more colorings than just picking all one color and doing that. For example, you could switch. Since this is the same thing, you can take the coloring for this over here and then make all this one color. That's another coloring. There's many coloring. Luke, you have a question?
Have you checked page 276 in the book? Have you been to Not Jokes and Pastimes?
Luke, this is highly inappropriate behavior. I'm not gonna chastise it, but let me just point out. You should not be reading not jokes. No not jokes in class.
These aren't even funny. These are awful jokes.
I'm afraid not.
All right. So let's see here. No not jokes in class.
And Pastime.
Okay, so here, let me give you 2 non-examples. This is important. Okay, so here's non-examples. So these are examples of things that aren't tricoloring. So I hope by now, I think it's pretty simple, I think, to understand why. But say you take this, and just to sort of make it clear, let's use red. I guess I could go like, ooh, make this red. It's not a tricolor. Well, notice there's only one strand here. I mean, it might be a little confusing for the definition of strand, but this counts as one strand. Now, why isn't this a tricoloring? Let's get some new hands here. Nodder?
Because you need at least 2 different colors for it to be tricolorable.
Okay, that's good. Blaze, did you have a different answer or the same answer?
The same answer.
Okay. Are you avoiding my trap? Yes?
I have a question. I know that that's the correct answer, but isn't that like a single color? So why doesn't it count?
Because tricoloring, you need at least 2 colors.
Didn't you say
You need more than one.
use one color?
No, add a crossing.
So does it satisfy in the second rule? Because
Yeah.
Right.
So that's a subtle thing, which is you might say, it's a second condition satisfied because the statement is at each crossing, but there's no crossing to talk about.
Mhm.
So this is a funny thing about math. Anytime you see a statement like at each crossing such and such, but there's no crossing, it's a true statement. Like if I were to say a true statement of that kind would be, all the chests of gold bricks in my house weigh over 4 tons. Now you might say, that's, what? Do you have any gold chests in your house? No, I don't. That's why it's an obviously true statement. So it's like every bad student in this class, right, is over 6 foot. But there's no bad students. So it's a true statement.
That's really good.
Yeah, so that's, for some reason that joke wasn't as funny to you guys. So like you don't just. Anyways, if you take another picture of the unknot with just one, how many strands are here?
1.
Just one. Okay. But there is a crossing. But I guess whatever I color, like red or whatever color I choose, here it's more obvious in some sense if you don't like that kind of logic, but it's valid logic, I should point out. There is one color at each crossing also, so it satisfies the second condition. It's all or one, right, at each crossing. But there's only one color still, so that's why these are non-examples.
What if you add another crossing?
Well, that's the question. So Nader I think is asking, what if I draw another diagram or projection of the unknot? If I make a more complicated picture of the unknot, can I then tricolor that? So I guess the answer is no. Okay.
And it's no because it's always going to be the.
No, it's no because it's not obvious and it's a theorem.
But isn't it because also that if you were to just tangle it up again, like that thing, like you did with the second example, like that was just like if you were just.
Well, there are many. Well, okay.
It's
You're
the
talking
same
about.
thing,
You're
though,
talking about. In this case, you could have applied a theorem. So what we're going to learn, what we're going to do is, we're going to prove that 3 Reidemeister moves preserve the property of the projection being tricolorable. So if the diagram's tricolorable and I do a Reidemeister move, it turns out the resulting projection's still tricolorable. Of course, there might be a different number of strands and all that, so it doesn't make sense to say it's the same tricoloring, but the property of it being tricolorable remains. So that's the theorem, which I'll state here. And it's not an obvious theorem, it's a theorem that needs to be checked. So, and you need to go through the cases and check it painstakingly. So THM, I guess, stands for theorem. Yes?
Is there a particular sequence of Reidemeister moves to transform the unknot thingy, like if it's more complex, or is it like a case-by-case basis?
Well, any diagram or projection of the unknot, there is a sequence of Reidemeister moves to bring it back to the simple circle. That's Reidemeister's theorem. But it's not obvious. In fact, that's really the crux of the whole business. It's not at all obvious. And maybe it might take like an exponentially, maybe it's like if you think of the function that if the projection you're giving has like n crossings, you might say how many moves does it take to simplify to this? It might be like 2 to the n kind of thing. You don't know, right? So it's not so obvious whether something can be simplified or not. So let's say the property of being tricolorable is preserved under Reidemeister moves. Okay, so that's a great theorem because I think colored chalk's a little weak. It's a little easy. I think that I'm a strong mathematician. Alright, so it's preserved. So in other words, another way to sort of state this is take any projection of the trefoil. It's connected to any other projection of the trefoil by Reidemeister moves. And if the property of being tricolorable is preserved under Reidemeister moves, then that implies every projection